Yesterday we finished talking about performance metrics that are commonly of interest to us as people who build networks or build network applications. So when you get a job, you may have to go and program an application that works on the internet. One thing you need to consider is the performance of your network and the performance of your application. And some of the metrics that are commonly used we've listed. Bandwidth, we haven't really explained much because it's going to be introduced in the next topic in a bit more detail. Data rate is the capacity of your link or channel, where the communications channel is where we send our data. For example, I connect my laptop to this PC via a single cable. The channel is the connection between the two computers. So the data rate depends upon my transmitting device, the transmitter in my laptop, the receiving device, the characteristics of the receiver, and the cable or the link. Typically, the bandwidth and the data rate are characteristics of the technology. That is, if you have to go and buy some technology, that is, you need to order for computers what type of technology to use for your network interface. Do you use Ethernet? Do you use wireless LAN? The bandwidth and the data rate are normally standardized. That is, you don't get to change them. They are a characteristic of the technology you choose. The throughput, so we can think of the bandwidth as the capacity, and sometimes called the capacity or even bit rate. The data rate, is sometimes called capacity or bit rate. The throughput is the real speed at which our data gets transferred across that link. If we have a data rate of 100 megabits per second, we send our bits at that speed across the link. But unfortunately, we're not always sending data that's of use to the user. If the user is the human user transferring the file, sometimes we need to send header, extra information, which is not the original file. That doesn't count towards the throughput. Sometimes we don't send anything at all. We'll see later when we look at individual protocols, we may send a little bit of data and then we have to wait for some acknowledgement to come back to say, yes, please send some more. So in that case, I send my data at 100 megabits per second and then my transmitter is not sending anything. So that means we spend some time not sending, which means our throughput goes down. So throughput's a measure of how much real data, or I sometimes call it user data, or real data that is successfully delivered to the destination. Successfully means sometimes I'll have to send some data, there'll be an error, I'll have to resend it. So in fact I've sent twice as much data, but only one of them count. The one that's successfully delivered counts towards the throughput. Data rate, the speed at which we send our bits. Throughput is the measure of how fast our real data is delivered. Always less than the data rate. Bandwidth and data rate are characteristics of our technology. You buy a technology for your network, you usually know what the bandwidth and data rate will be. Throughput varies. It depends upon the applications, the protocols being used. So it's not known in advance usually. And it's harder to determine accurately. We either need to measure it or do some calculations to find an approximate throughput. And the calculation we did yesterday quickly gave us a very simple example of getting an approximate throughput. We'll return to it and do the second part of it, or the part that I asked you to do for homework. That is, we have a two-layer protocol architecture. This was a quiz question, so it was set up so it was very simple. You'll see in some quizzes and exams, the data or the setup of the question, a two-layer architecture, 20-byte header and so on, may not be realistic. Okay? Because I use 20-byte, even though I use 20-byte header here, it may not be true in real protocols. It's just a number to make it a little bit easier to calculate in a quiz or an exam. So in this case, we had a very simple two protocols. We add some headers, transmit our data. There's no concept of retransmissions. There are no errors, so there's no overheads due to that. The only overheads in this example are due to the headers. So if we have a data rate of 1 megabit per second, the throughput is going to be slightly less, and it's going to depend entirely on how much extra information we need to send in the headers compared to the real user data, the 10,000 bytes the user wants to deliver. What do we get up to? I said try and modify this question where instead of segments containing 3,000 bytes, they contain only 300 bytes. Where does this come from, or where does this segmentation come from? It turns out that most protocols will have a limit on how much they will send at any one time across a link. I have a 1 gigabyte file to send from my computer to this computer. The protocols are not going to send that 1 gigabyte all at once. What they'll do is they'll break it up into smaller segments and send a small segment of, say, 1,000 bytes and then another segment of 1,000 bytes. Send it parts at a time. The reason for doing this, or one reason, is if there's an error. If I send that 1 gigabyte all at once across the link, then the receiver checks the 1 gigabyte file and it finds of that 1 gigabyte, which is what, 8 gigabits, 8 billion bits, it finds that 1 bit is in error, is wrong. There's a small mistake. Then the file is of no use. Of those 8 billion bits, only 1 bit is wrong, but still the file is incorrect. So we need to retransmit that 1 gigabyte file again. So this computer may say, at the protocol level, say, the file that you sent me, or the data that you sent me, has an error, please retransmit. So I'd retransmit a 1 gigabyte file again. That's if I transmit the 1 gigabyte all at once. If I break it into segments, though, I transmit 1,000 bytes, and then another 1,000 bytes, and then the next 1,000 bytes. And then the receiver, of those many segments that it receives, it discovers of one segment, there's 1 bit in error, then it can tell the sender, please retransmit just that one segment. You do not have to send the entire file again. You only need to send a small part of that file. And once we get that small part, we have the correct file at the receiver. So most protocols will have a limit, an upper limit on the amount of data that they can send in each packet. We'll see that when we look at some individual protocols, the different realistic values. In the first case, we said 3,000 bytes. What if it's 300 bytes? Then we start with 10,000 bytes of real data or user data. That is the information that the user wants to transfer across the network. The first layer adds a 20 byte header. So we have 10,020 bytes in total. Does its processing and sends that 10,020 bytes down to the next layer. So this was the, if we draw our layers here again, we have the top. I don't know what I called them yesterday, application and physical, but just the top and the bottom layer. The user data is generated. The top layer adds a header, sends all of that to the next layer, the bottom layer in this case. And then according to our rules, it breaks it into segments such that they're no larger than, and in this case, let's set the maximum size to be 300 bytes. When we used 3,000 bytes yesterday, we did some calculations, and do I have the answers somewhere? Yesterday, when we used 3,000 bytes, we did some calculations and we come up with a throughput of about 994,000 bits per second. of when we had a 1 megabit per second link, we use about 99.4% of that link for the transferring the real data. That is a throughput of 994,000 or 0.994 megabits per second. That was yesterday. When we have 300 byte segments, we have this 10,020 bytes and we need to break it into segments no larger than 300 bytes. We have the first segment and then the next one, and then how many segments do we have? Anyone? Some people calculated the answer yesterday. Anyone else? 340? Okay. How many of the size of 300 bytes? If we have three of these, then yeah. If we have 33, and you can do the calculation, but if we have 33, then that brings us up to, what is it, 9,000. If this is the first, the second, this is the 33rd, that'll be 9,900 bytes in total. Okay, 300, 600, 33rd would be 9,900 bytes. And the last one, we have 10,020 would be, what, 120 bytes. The first 33 can take up the full size of 300. That's the maximum size. 33 times 300 is 9,900. We have a total of 10,020. So the last one is going to be 120 to bring 120 plus 9,900 is 10,020. So this would be the, let's say, the 34th segment, a smaller one. Each segment has a header attached to it. Again, 10 bytes. And then we transmit one at a time across the link. So we transmit this 310 bytes, and then immediately after transmit the next 310 bytes and the next, and so on. The receiver will receive them, remove the header, check everything's okay, join them back together again, so we get this, and then pass up and remove the header, and eventually the receiver will receive the 10,000 bytes. So the source segments or fragments the data into smaller segments. The receiver reassembles. So we sometimes call it fragmentation and reassembly, or segmentation and reassembly. We break it into smaller chunks and then put them back together at the receiver. And coming back to that reason why, if we send these 34 segments across the link, and unluckily it turns out that there's one bit that's in error when we transmit across the link, and it's a bit in this second segment, just one bit in this 310 bytes is wrong, then in the ideal case, the receiver would recognize that there's one bit in error and ask the sender to send that one segment again. Just send segment number 2. Segment number 1 and 3 up to 34 are all okay, but there's something wrong with segment 2. Please send that again. And if it works the next time, the receiver's received all the data successfully. That's the advantage of breaking into segments. What's the disadvantage of breaking into segments? The process of segmentation takes some time, some processing time. Yeah, that's one thing. The header, the total amount of header is going to be larger. Yesterday, when we broke it into 300 byte segments, the total amount of data we had when we calculated was 10,060 bytes. That is, we had 60 bytes extra of header. Now we have how much? What's the total number of bytes we transmit? How many? The total number of bytes we transmit, or what's the total number of header bytes we transmit? 10,360. How did he calculate that? 10,360. Where does that come from?
It's come from the 4 segments combined together.
How many segments?
In this case, it's
34 in this case. 34 segments, each have 10 bytes of header. So I've only drawn 4 here, but there are 34 here. Each have 10 bytes of header. That's 340 bytes of header, plus this 20, a total of 360. So the total we send is 10,360 bytes. By breaking into smaller size segments, we increase the overhead. 360 bytes of overhead, as opposed to yesterday with a larger segment, 60 bytes of overhead. Increased overhead will mean lower throughput. How long does it take to transmit? We just look at the amount of bytes we need to transmit and the rate at which we transmit. We have 10,360 bytes, and the rate at which we're transmitting is 1 megabit per second. Have I calculated it? I think it's that. You'll check me. Bits, convert bytes to bits at 1 million bits per second. And you'll do the calculation and you get 82.88 milliseconds. Lowercase m, milli, uppercase m, mega. Don't get confused, even though it's harder to see on the board. That's an uppercase m, this is lowercase m. So that's the time it takes to transmit our data, or all the bytes, the total amount of data that we need to communicate across the link. From the user's perspective, it takes 82.88 milliseconds to transmit their data. And the amount of data they get transmitted and delivered to the destination is 10,000 bytes. So from the user's perspective, they get 10,000 bytes delivered, and it takes them 82.88 milliseconds to do so. And that gives us our throughput. And it turns out to be 965,250 bits per second. Same approach to the calculation as yesterday. We've just got a different segment size. Any questions on those steps? confirm with your own calculator the calculations if you like, that's okay. Sometimes I make mistakes, but I think someone yesterday got the same value. And lower than yesterday. 994,000, 965,000, slightly lower. Only because of the smaller maximum segment size. The more header is contributed. So that's an example of the relationship between the data rate, the speed at which we send bits across the link, and the throughput as experienced by the user. This is the simplest example that we'll see. In real life, not only are there more layers, but it's not just headers that contribute to the overhead. As I've said, in some cases we may need to retransmit. We send one part, one segment, and we'll have to send it again because there's an error. That takes time. Effectively, that increases the total time to transmit. If this goes up, if we spend more time here, throughput will go down. And some protocols require acknowledgements to come back. I send a segment and then wait for an acknowledgement. Again, the time to transmit all the data goes up. Our throughput goes down. So the calculation becomes more complex. We will see some of them at a later date, the more complex calculations. Any questions on bandwidth, which we haven't really said much about, data rate and throughput? Three performance metrics that are important when we select networks or build applications. There's one quiz this week, just one quiz. It's already available. It's due next Wednesday, and it has some of these calculations. I think you're allocated 30 minutes for this quiz. It's a quiz where you need to do calculations such as this. So take a piece of paper or make sure your calculator's there, because it's not just true or false, multiple choice. There's some calculations there. Another key performance metric is delay. How long does it take to get information from one computer to another? The time to transmit. Now, it's related to throughput, but different applications have different requirements in terms of delay and throughput. For example, you download a large file. You've got a 5 gigabyte file to download. Which performance metric do you care about, delay or throughput? If I let you choose one of them, you want to maximize delay or maximize throughput or minimize delay. Which one is most important when you download a file? You've got a very large file to download. You want to leave it running overnight because it's going to take a long time. What do you care about? Throughput is important because you have a large file, 5 gigabytes. This time it's going to take to download is going to depend upon the speed at which you can download, the throughput. Okay? The delay is the measure of how long it takes. We normally think how long it takes to get one packet from source to destination. We'll go through some examples to illustrate delay, and we'll see how it's important. It's important when it's not so much the size of the data that's important, but the response time, for example. Web browsing. You send a request to a server, the server sends back a page. The time it takes to get to the server and get back impacts on your response time in terms of the web browser, the delay across the network is going to be important in that case. Delay, how do we explain it? Units are seconds, okay, we're measuring time. There are 4 main components to delay. Transmission delay, the time it takes your computer to send bits out of your computer onto the link to transmit. Propagation delay is the time it takes for a bit, or more precisely a signal, to propagate across a link. Processing delay is the time it takes your computer or intermediate devices to process in memory by the CPU inside that computer. And queuing delay, also inside computers, is the time that some parts of the data may have to wait for other data. We need to try and explain those 4 components, and we'll see how we can combine them to get the total delay. Let's say, for the first 2 components at least, to explain them, we'll use an example. What do you do if there's a fire? I don't know if there's even fire alarms in here, but if there was a fire alarm, what do you do? Run? Run where? Run to the room on the other side of the corridor? Run downstairs? Okay. If we were organised, then it's better not everyone just runs to the door, because there'll be a jam at the door. People will fall over and hurt themselves. So maybe what should happen is, as I'm the lecturer here, I would go to the door and let you out one at a time, okay? And you would then follow to the corridor and downstairs and go outside to some grassed area, okay? And the time it takes us to do this is important. We'd like to minimise the delay from getting this class out of this building and out into the safe area outside. So let's think about the components that contribute to the delay, the time it takes you or us to get out of the room and down into some safe area outside. I want to do it in an orderly manner. That is, I don't want everyone to rush to the door and hurt yourselves. So I'm going to say that what you need to do, I'm going to stand at the door and let you go one at a time, okay? And 1 person fits through the door at a time. And so you all come to the door and I'll just let, okay, 1 person, next person, and so on. Let's say I do that and it takes me some time. I can let out 1 person per second. Okay, so 1 person per second can get out the door. And then when a person gets out the door, they walk fastly. They don't run, they may fall over. They walk fastly down the corridor, down the stairs, and so on. How fast are you walking if you walk fastly? How fast? How many meters per second, how many kilometres per hour do you think you're going? 2 meters per second, maybe? So the speed at which you're moving, let's say everyone, they go out 1 at a time and you stay in order because you're all nice people. You don't push someone over or go past them. You stay in order. And let's say that you walk at a speed of, or you go a bit faster, 3 meters per second. Okay, you're almost running, but 1 at a time in single file out the door. And you've got to go downstairs and some space outside where it's safe. Maybe the distance is, I don't know, 150 metres by the time you get outside. So once you get that 150 metres, then everyone's safe. Okay? So what we care about is how long does it take to get this class into a safe location outside. Can we calculate it? How long, from my perspective, how long does it take you all to get outside in the safe area? Calculate it. Let's say, and 450 seconds. I think some of you will burn if it takes so long. Too long. No? Let's see. Another thing we need to know, how many people are in the class? Well, not so many today, but normally there should be about 40 people. Say we have 40, normally 40 students in the class. How long does it take to get the class out into the safe area? $50 seconds, 450, 200. How would you calculate it? Well, there's two components here. There's the starting component, getting you out the door. Okay, that's the first step. There's some limit as to how fast we can get you out the door. And then there's the component of you propagating down the corridor, down the steps and outside, which depends upon your speed. How fast can you get out the door? The first person, well, one person per second. So every 1 second, one person gets out the door. How long does it take to get the entire class out the door? How many? 40 seconds to get the entire class out the door. Because what I do is the first person goes out, one person per second, 1 second later, the second person is I let them out, and then the next one and so on. Okay? So we have 40 people. It's going to take 40 seconds to, I'll say, to transmit you out the door, to get you out of the class. Now, consider yourself. As soon as you get out that door, how long is it going to take you to get downstairs to the safe area? Just you, just one person. 50 seconds. We have a distance of 150 metres. We have a speed, you're travelling at a speed of 3 metres per second, so it's going to take you, the individual person, 50 seconds to get down the stairs and then outside. We say that you're propagate. That's the time it takes an individual person to get down the stairs and propagate through the corridors, down the stairs and outside. If we can try and draw this, what happens over time? I'll try and draw and capture this. This represents time. So, time. Start at time 0. That is, we start this event at time 0, and I'll increase time as we go down, we'll record. And what I'm going to show in this diagram, that a person goes out. So the first person, you don't have to draw this, the first person is propagated out the door. So we have all our 40 people here waiting to go, our 40 people. Let's first consider how long it takes them to get out the door. Well, we've calculated 40 seconds. That is, I let one person out, 1 second later the next person goes out, 1 second later the next one, and so on. So at time 0, the first person goes, 1 second later the next person, the third person, and so on. And after 40 seconds, all 40 of you have left the room. So from my perspective, my job is to get you out the room. Your job is to walk down the stairs. From my perspective, after 40 seconds, you're all out of the room and done. Now, once a person is outside of the room, they need to propagate down the stairs, walk down the stairs. It takes some time. And what I'm going to draw here is another line. So this is you in the room. This is the area that you need to get to. You start walking at time 0. You get out the door. The first person starts walking at time 0. after, or at what time does the first person arrive at the destination outside? At time 50. The first person starts walking at time 0. They take 50 seconds to walk to the destination. So what I'll draw is, okay, it may not be to scale. At time 50, again, this is still at time 0. At time 50, the first person arrives at the destination. The second person follows immediately, or 1 second after. When do they get to the destination, the second person? They start walking at time 1 and they arrive 51, 1 second later. Because again, you start walking at time 1, it takes 50 seconds to get there, you'll arrive at time 51. When's the last person finally arrive at the destination? At time 90. They start walking and arrive at 90. The total delay in this case, ignoring other factors, if it takes 40 seconds to get you all out the door and 50 seconds for an individual to get downstairs, it will take a total of 90 seconds before everyone is safe outside. So in this case, the total delay is made up of the time to transmit you out the door and the time for an individual person to propagate through the corridor and down the stairs, to walk down the stairs. Any questions on that? This is just simple physics, perhaps. Now, you are not a person, you're a bit. And we're not sending you out the room, but we're sending you out of a computer. The same concept applies. My computer has 40 bits of data to send. My device can transmit at some speed at 1 bit per second, for example. And each bit needs to travel across a link. So if I connect my two computers together, we can imagine the bit, or the signal representing the bit, comes out of the computer, and then because it's an electrical signal, it propagates across the link. And depending upon the distance of the link, in meters, it takes some time to propagate. The propagation delay of that bit, or the signal representing the bit. The same concept applies. We transmit our bits out of a computer, and a bit propagates across a link, or across a network. The total delay of transmitting all of those bits and propagating them is the sum of the transmission time, or transmission delay, and the propagation delay. We'll come to an example in a moment. Because we see what's happening here, there's some things happening in parallel. Once the first person is transmitted out the door, they are walking. At the same time that they are walking, the next one is being transmitted. You can think that that's happening at the same time. This person is walking, they're halfway through down the stairs. At the same time, another one is coming out the door and they're walking, and you find that the people form a line down the corridor. The 40 people have a single file line down the corridor. The same when we transmit bits out of our computer. We transmit a bit at a time. In the simplest terms, we transmit a signal representing 1 bit at a time. The first bit is transmitted out of the computer. It propagates across a link. At the time when that's propagating across the link, the second bit is transmitted out of the computer and starts following it. And the third bit comes out of the computer and is following the second one, and so on. And all those bits propagate across a link until they reach a destination. So we have what's called the transmission delay or transmission time, the time to get the bits out of the computer, and the propagation delay or propagation time, the time for an individual bit to propagate across a link. For our people, the transmission time depended upon what? The number of people, 40, divided by the rate at which we could transmit them. It was 40 divided by 1 per second. That's how we calculated 40 seconds. The propagation time depended upon the distance at which we need to propagate and the speed at which we propagate. In our case, and the speed at which we walk. It was 150 metres divided by 3 metres per second. The same is used to calculate transmission and propagation delay in link for data. The transmission delay depends upon the number of bits we have to transmit. 40 bits, 1 million bits, whatever the size of the data is, and the rate at which we transmit. 1 megabit per second, 10 gigabits per second, the transmission rate, the data rate. We calculated that in the previous example. We had our 10,060 bytes, the number of bits, divided by the rate of 1 megabit per second, and we got a transmission time or transmission delay. The propagation delay depends upon the distance that the bits need to propagate. They need to travel. That is the length of the link in metres or kilometres, and the speed at which bits propagate. The bits are actually signals, say some electrical signal passing through some wire. What's the maximum speed at which they can propagate? How fast can we send electricity through a copper wire? How fast can I send a radio signal through the air from my laptop to the access point? In general. The speed of sending a signal, you're thinking about the rate at which we can transmit bits out of my computer. But once we have some, now think back very basic physics, once we have an electrical signal, some radio signal, any signal, some sine wave or whatever, how fast can it propagate across some medium? Maybe the easiest one to think of, the light from here to my eyes, the medium is the air. How fast can it propagate from when it comes out of the light bulb and reaches my eye? People are mentioning 3 by 10, the speed of light, okay, 3 by 10 to the power of 8 metres per second. That's the upper limit in the speed at which signals can propagate. The speed of light. Nothing will go faster. 3 by 10 to the 8 metres per second approximately. In fact, when you have an electrical signal across a copper wire, it may be slightly less. Maybe it's 2 point something by 10 to the 8 metres per second. I don't know what it is. But in the order of 200 million, 300 million metres per second. That's the typical speed at which our signals propagate. And in this course, unless I tell you otherwise, you can assume the speed of light. And you can assume that the speed of light, so the speed, sometimes I'll tell you it's a specific value, but otherwise, the speed of light, which is sometimes written as c, 3 by 10 to the 8 metres per second. 300 million metres per second is the speed here. So for transmission delay, we need to know the amount of data we need to send, the number of bits, the rate at which my device can transmit, and that's where someone mentioned my LAN card can transmit at 100 megabits per second, so that's the rate. The distance between source and destination, which is the length of the link. If it's just two computers connected together, it's across 2 meters, the distance is 2 meters. And the speed of light in most cases, for simplicity. Let's do a calculation just to confirm that. I have a link between two computers. The source and destination, A to B. Let's say, and just to keep the numbers simple, the data rate, that is the speed at the rate at which my computer A can transmit, it depends upon the transmitting device, the receiving device, and the link. Normally when you buy a technology, that's a fixed value. Sometimes you can vary. For example, my wired LAN, 100 megabits per second. In this example, 10 kilobits per second. I have some data to send. 50 kilobytes. And the distance between A and B is, it's across, say, between our campus and the Rangsit campus, it's 15 kilometres. What's the delay to send this 50 kilobytes of data from A to B? How long does it take before all of the data is received at computer B? Try and calculate that. Considering just the transmission and propagation delay. We'll come to the other two later. Try and find the total delay to get my 10,000 byte file from A to B. Think about transmission delay and propagation delay using this information. Any answers? People are good at drawing the diagrams, copying the diagram. Let's see some calculations.
Speed of light again.
The speed of light.
Yeah. Why did you use the speed of light in this example?
Why?
Yeah.
Why did I use the speed of light? Because when I say we transmit a bit across the link, so the source computer creates a bit and transmits it across the link to the destination, what is that bit? It's represented by some signal. Okay? Some, if it's wireless transmission, some radio signal, some electrical signal. And in terms of basic physics, when we send some signal, so don't no longer think about bits, but think about sending some signal, some electricity, we think of some waveform. Say, let's think of a sine wave. We start transmitting that waveform, it propagates at some speed. And the maximum speed at any signal can propagate, which is light, is the speed of light. Electrical signals across copper may be slightly slower, but for simplicity we assume the speed of light, at least in this case. Our bits are represented by signals. Make sure your units are consistent. 50 kilobytes, 15 kilometers, 10 kilobits per second.
What is the rate for time this?
Sorry?
The rate.
The
for
rate,
time this
which one do you think?
long below.
10 kilobits per second, yeah. So the transmission delay is about transmitting the bits, the number of bits at some speed, depending upon your transmitting device, the rate at which it transmits. The propagation delay is about physics. How long does it take a signal to propagate across some distance? It depends upon the distance that that signal needs to propagate and the speed at which that signal propagates. See some answers. Check 5. No. Check your units. You remember there's both transmission delay and propagation delay. There are two components. Calculate them both first.
What we do is the data,
Yeah, number of bits is the data.
but we have to say that to first.
Yep.
15 QB is a rate, and what is the speed?
What's the maximum speed that you can send a signal? What's the speed from which the signal from that light reaches your eyes? That's the upper limit, at least. Now, check and find the total delay. You're on the right track. Possibly, I don't think, I'll have to check, but I think this value is too small. What have we got? 50. I think so, yeah. Yeah, I think you're close. I don't have the answers. Is the units correct? What is it? 15. I think close. When I do it on the board, I'll confirm. I don't have the answer. Some people are getting close, I think. I don't know the answer. I have to calculate it myself. First, let's find the transmission delay. Two components. How do we calculate transmission delay? The data size, or the number of bits, divided by the data rate, the rate at which we transmit. The data size in our case is 50 kilobytes. So the data size, the number of bits, divided by the rate at which I transmit those bits, 10 kilobits per second. And here we have bytes, here we have bits per second. So 50 times 8 is 400 kilobits, 400,000 bits, divided by 10 kilobits per second, 10,000 bits per second. 40 seconds. I think several people have got that, 40 seconds. And then the second component, propagation delay. Time to propagate. I have a signal. Just think now just of 1 bit. To transmit it across a link, think of it as, say, a sine wave, a signal, just the start of that sine wave. That sine wave propagates. It takes time. That's the signal, and the time it takes depends upon how far it needs to travel and the speed at which it travels. The distance that my signal needs to travel is 15 kilometres. And we're going to assume that the speed at which it travels is the speed of light. That is, that we have some signal. The maximum speed any signal can travel, light, radio, is the speed of light. In practice, we're normally less than that, but for simplicity, let's assume the speed of light. What is the answer? 15,000 divided by 300 million. Fifteen is 5. Who got that? Anyone? Maybe I'm wrong by order of magnitude there. Who got an answer with a calculator? 50 microseconds? Yes, yes. 50 microseconds. That is 50 by 10 to the power of minus 6 seconds. Or 0.00005 seconds. And we calculate the total delay as just the sum of those two components, which is this 40.00005 seconds. Just add those two values together. It's the same as what we did when we calculated people walking out the door and down to the ground floor. We're transmitting bits one at a time, and those bits are propagating as signals one at a time, following each other across the link. That wasn't the example that I wanted to show you. Well, it wasn't the right answer that I wanted to show you. It's the correct answer, but that's okay. It's not the best example. And that's how we calculate transmission and propagation delay in practice. So you need to remember essentially the equations, where you understand this is the number of bits, or that sometimes you'll see the data size divided by data rate, distance divided by transmission signal speed. Remember, propagation is about physics. The time for you to walk from this room downstairs depends upon the distance and the speed at which you walk. The transmission delay depends upon the capabilities of your transmitter and the amount of data you have to transmit. Any questions either on the calculations or about the concepts of transmission and propagation delay? We're only halfway there. We've covered 2 components of delay. There are 2 more to cover. But we'll see that in terms of your perspective, they're a bit simpler and that we don't calculate them. Any questions about propagation or transmission? Easy. There are other components of delay. I don't know if we'll go very well with our original example, but let's say that for me to send you out the door, not only is it depend upon how many people can get out the door, but before I send you, I need to record your name so I know who is left. Okay? So I need to ask you your name, write down your name. That takes me an extra 2 seconds. We would consider that processing delay, the time to process the data before it's sent. That is the processing of the data inside a computer. The last component of delay is queuing delay. You walk down. Of course, you're not the only people who are leaving the building. Other classes are leaving. When you all start arriving at the exit door, the door that leaves the building, you need to form a queue because only one person can fit out the door at a time. So someone arrives from this class and then someone from another class arrives. So the second person from this class will have to wait for that person from the other class to get out the door. You'll start forming a queue to get out the door. That time that you spend queuing, waiting for other data to be processed, to be sent, is queuing delay. We don't normally calculate these. Processing delay in terms of data communications depends upon the capabilities of our computers, the transmitting and receiving devices and intermediate devices. I create a 50 kilobyte file in my application. I press send on my application. Then my computer goes to work and does some processing on it. The protocols go to work. That takes time. So the time spent processing the data you can think is inside the computer. What does it depend upon? How long does it take your mobile phone to process 50 kilobytes of data? And how long does it take your PC to process the same amount of data? What does it depend upon? Do you think your mobile phone will be faster than your PC? Unlikely. Why not? Processor, the CPU, different speeds, RAM speed, hard drive speed, all those factors of how fast a computer is. That's what processing time comes from. How long does it take to process the data? That is, how long does it take all the protocols to do their work? Very hard to calculate. That is, it depends on many different factors. One computer could be completely different from another computer. In this class, we will not attempt to calculate it. Sometimes we will say, or I'll say in a question, assume the processing delay is some value, e.g. 1 microsecond. The processing delay, think of inside the device. Assume both A and B have a processing delay of 1 microsecond here, an additional 1 microsecond here. Then our total delay is not just transmission plus propagation, we also must add in the processing delay. If in our original question it was an extra 1 microsecond, this is a mu in fact, it's not m, this is micro, 10 to the power minus 6. Sorry if it's not clear on the board, mu. 1 microsecond here, 1 microsecond here. The total would be, instead of this, would be 40.00052 seconds. Extra 2 microseconds, which is very small in this example. This was 50 microseconds plus 2 microseconds. because we need to process in this computer and in this computer. Assuming we knew the processing delay. I will not ask you to calculate processing delay. I would give it to you because it depends on many different factors.
So we insert 2 microseconds.
No, no, I will give you the value. If I don't give you a value, what are you going to assume?
What is that?
This is, we have milli and we have micro. Milli M, that's a U, or the Greek letter is mu. It looks like a U in English, micro. If I don't give you the processing delay in a question, I don't say anything about it, assume it's 0. Normally it's very small compared to the other parts. In this question it's very small, but in practice, the time it takes your computer to process the data is usually, not always, but most times very small compared to the time to transmit and propagate. Normally processing delay is very small. So often we ignore it and say, okay, it's very small, it's close enough to 0 that we won't include it. So unless I tell you the value, you can assume processing delay is 0. There's no equation to calculate it. And the last delay component is queuing. Sometimes there's an E in there. This is, our example won't capture it, but let's say we need to send across a network from one computer to another computer via some intermediate computer. From A sending to B. It's possible what we do is we send our data to here and then this one sends it on to B. Transmission delay, we calculate the transmission delay for this computer to transmit the data out. Propagation delay depends upon the distance of this link. Processing delay depends upon the speed at which A, the intermediate computer, and B process. Note that transmission delay the transmission and propagation delay across a single link. That is, we'd have a transmission delay across the first link. We could calculate that if we knew the characteristics. A propagation delay. We transmit that data to this intermediate computer, let's say C, and then if that computer transmits again onto B, we have a separate transmission delay here. Transmit, propagate. So think of transmission delay and propagation delay is for every link in our network. If we have multiple links, you need to calculate it for each of them. The total delay is the sum of them all. Processing is inside a computer. We cannot calculate it, even in the intermediate value computers. Queuing delay is if we transmit our data to C, but there are other people transmitting to C as well. What may happen, data arrives at C from us and from other computers all at the same time. They are stored in memory inside C, in the memory or in a queue, and one of them is transmitted at a time out. So if I transmit to C and 2 other computers also transmit to C at the same time, C receives 3 messages, 3 packets. It can only transmit 1 at a time to B. So it transmits the first of those 3 and the other 2 have to wait in a queue until they are transmitted. So transmit the first packet, the second packet waits for that to be transmitted, so there's some queuing delay. Then the second packet is transmitted. The third packet also had to wait. That also has some queuing delay, and that's transmitted. So in such a scenario, there may be extra delay of packets or data is queued inside a computer. Queuing delay, again, I will not ask you to calculate. There is a whole theory of mathematics for how to calculate queuing delay, but for this course we will not cover that. Again, I will either give you a value, e.g. the queuing delay is 5 seconds, or if there's no value given, assume it's 0. Okay? So think of transmission and propagation delay across links. Each link may have their own transmit and propagation delay. Processing delay inside devices, so is queuing delay. I'll just write Q. Normally inside intermediate devices, but it's possible, less common, to be in end devices. The simplest way is to remember transmission and propagation for links, processing and queuing for computers. And total delay, which is what we care about in the end, how long does it take to get my packet from here to here, is the sum of all the components. Delay is additive. If you can calculate all these values, then the total delay is just the addition of all of them. Almost done. You'll practice with some examples for the quiz. There's, I think, 1 or 2 questions about delay, easy calculations. You need to be able to calculate transmission delay. You need to be able to calculate propagation delay. There's no calculation of processing or queuing delay, but for example, if I give you a scenario and I tell you the values of queuing and processing, you need to be able to calculate the total delay, which is simply the addition of all the components. Remembering that queuing and processing apply to computers, transmission and propagation apply to links. If you have a scenario like this, then it's queuing plus processing plus transmission across the first link plus propagation across the first link plus queuing plus processing plus transmission across the second link plus propagation across the second link plus queuing plus processing gives you the total delay, whatever those values are. And that applies if there's 2 links, 1 link, 1 million links. Okay, you can expand, apply that concept to any network. I think the best way is to practice some calculations, and you'll get that in the quiz. Packet delay variation we will talk about at a later stage. Let's stop there. Next week we'll move on to the physical layer and explain how do we represent bits as signals. I've already spoke about signals. How do we represent bits as signals to transmit signals across a link? Just one quiz this week, due Wednesday morning, 8:30, quiz number 4. It's some calculations based on these concepts.